November 12, 1942, 3:30 hours. Richmond, California. At Shipyard No. 2 of Permanente Metals Corporation, a 441-foot cargo vessel stood complete under floodlights, its steel hull weighing over 28,000 tons. Henry J. Kaiser, a man who had never built a ship before 1940, walked along the platform watching workers step back from the finished structure. Around him stood more than 1,000 laborers, former clerks, farmers, housewives, many trained in welding just weeks earlier. He did not yet know that within hours this ship, SS Robert E. Perry, would shatter 3,000 years of shipbuilding tradition and redefine industrial warfare. Within 2 years, this same system would produce thousands of vessels, tipping the balance of the Atlantic and deciding the logistics of global war. At that moment, the global maritime establishment believed one thing with absolute certainty. Complex ships required time, craftsmanship, and generational expertise. Traditional shipyards had spent 6 to 8 months constructing vessels of similar size, relying on skilled riveters who installed up to 1 million rivets per ship at a rate of roughly 100 per day per crew. Naval architects like William Francis Gibbs insisted that precision and experience were irreplaceable. Even the United States Maritime Commission doubted that speed could coexist with structural integrity. Their logic was grounded in centuries of accumulated knowledge. Ships were not machines to be assembled, they were structures to be crafted. On paper, however, a different system had already taken shape. Kaiser's shipyards operated not as traditional maritime facilities but as industrial production networks. The system included 7 parallel building ways enabling simultaneous assembly, prefabrication zones producing sections up to 150 tons, over 10,000 workers, fewer than 2% with prior shipbuilding experience, overhead cranes every 100 feet for rapid placement, simplified blueprints replacing detailed schematics. All calculations pointed to one outcome. Parallel production would reduce build time from 230 days to under 70, and eventually far less. The ship was no longer built step by step, it was assembled like a machine. Then came the first signs that something unprecedented was happening. Construction times began collapsing at a rate that defied engineering logic. Ship 1 required 197 days. Ship 5 dropped to 128. Ship 10 fell to 97. By early 1942, average production reached 70 days, already a 70% reduction. Traditional shipyards dismissed it as an anomaly. Yet reports continued. Prefabricated engines installed in hours instead of weeks, hull sections assembled simultaneously instead of sequentially, and untrained workers outperforming experienced craftsmen. At first, it seemed like statistical noise. Then the scale became undeniable. What observers saw in Richmond on November 12 did not fit any known industrial model. Not months, not weeks. For days, 15 hours, and 29 minutes. A complete ocean-going vessel assembled, launched, and prepared for service. Thousands of components aligned perfectly under a system that eliminated traditional bottlenecks. Entire cargo holds, engine rooms, and deck structures dropped into place with crane precision. This was not acceleration, it was transformation. With each hour, the implications expanded beyond shipbuilding. Reports from across American yards showed identical patterns. Production times collapsing across 18 shipyards, workforce scaling to 196,000 workers, over 40,000 women entering industrial roles, construction costs dropping to $1.8 million per vessel, output reaching 3 ships per day nationally. The system was no longer experimental, it was industrialized warfare. Germany's U-boat campaign was sinking millions of tons annually, but American production was beginning to exceed those losses. The core problem became clear through contrast. Traditional shipbuilding relied on skilled labor trained over 4 to 10 years, sequential construction processes, rigid engineering specifications. Kaiser's system operated with workers trained in 2 to 6 weeks, parallel assembly across multiple zones, simplified, adaptable designs. This was a collision between craftsmanship and industrial scale. One optimized for perfection, the other for volume. It was in this moment that Emery S. Land recognized what others had not. The breakthrough was not speed alone, it was the elimination of constraints. Ships were no longer products of expertise but outputs of systems. Production had shifted from skill to organization. The conclusion was unavoidable. The side that could build faster than losses occurred would dominate the war. By mid-1943, the outcome was visible in numbers. Over 2,400 Liberty ships had been produced across American yards. Construction time averaged 42 days. By 1945, total production reached 2,710 vessels, delivering more than 53 million tons of shipping capacity. Loss rates remained at just 7.4%, proving the system's reliability. Ships designed for 5-year service lasted decades, with some still operational 80 years later. This story revealed a fundamental truth of modern warfare. Victory is not determined solely by tactics or battlefield brilliance, but by production capacity and industrial organization. Armies fight battles, but industries decide wars. The Liberty ships did not just carry cargo, they carried the mathematical certainty of Allied victory. December 27, 1940, Washington, D.C., inside the offices of the United States Maritime Commission, Henry J. Kaiser signed a contract that stunned every established shipbuilder in the country. A 58-year-old construction magnate, whose entire career had been spent pouring concrete and moving earth for dams across the American West, committed to delivering 30 ocean-going cargo ships within 2 years. He had never managed a shipyard, never designed a vessel, and had no experience with maritime engineering. Around him, industry veterans watched with quiet skepticism, convinced that within months the project would collapse under the weight of its own inexperience. None of them yet understood that this ignorance of tradition would become the decisive advantage. Within 18 months, the same outsider would dismantle centuries of shipbuilding doctrine and replace it with a system capable of outproducing the rest of the world combined. At that moment, American and British planners believed one thing remained certain: the Battle of the Atlantic would be decided by tonnage loss. German U-boats were sinking Allied shipping faster than it could be replaced, with approximately 3.6 million tons lost in 1941 alone. Britain's survival depended on maintaining supply lines across the ocean, yet traditional shipyards required an average of 230 days to complete a single cargo vessel. Even at maximum output, existing capacity could not compensate for losses. The expectation was clear: unless production increased incrementally, the Allies would face logistical collapse within 2 years. Kaiser's promise was therefore not seen as innovation, but desperation. On paper, the industrial system Kaiser began assembling in 1941 appeared chaotic, even irrational. The design eliminated nearly every principle of classical shipbuilding. It included complete abandonment of riveting, replacing 1 million rivets per ship with welded seams, prefabrication of entire ship sections constructed simultaneously across multiple zones, workforce expansion to over 10,000 workers in a single yard, with fewer than 200 experienced, crane systems capable of lifting 150-ton modules into place, simplified blueprints that reduced engineering detail in favor of speed. All projections from traditional engineers predicted structural failure, inefficiency, and delays. Yet the expected result from Kaiser's calculations was radically different: a reduction in construction time by more than 70%, achieved through parallelization rather than craftsmanship. The first warning signs emerged during early production cycles in 1941. Kaiser's engineers, led by Clay Bedford, applied assembly line logic borrowed from automotive manufacturing, particularly methods observed at the Ford Motor Company. Instead of building ships from keel to deck in strict sequence, they constructed bow sections, stern sections, engine compartments, and deck houses simultaneously. Engines weighing 140 tons were assembled off-site and installed in a single operation rather than over weeks inside confined hull spaces. Traditional supervisors reviewing these methods reported inconsistencies, incomplete drawings, and apparent disorder. Initially, these deviations were dismissed as inefficiencies that would inevitably slow production. Then the results began to contradict every expectation. Construction times dropped at a rate that could not be explained by incremental improvement. The second Liberty ship required 169 days. By the fifth, it fell to 128. By the 10th, 97 days. By early 1942, Kaiser's yards averaged 70 days per ship, matching or exceeding the performance of the most experienced shipyards in America. The scale of change was no longer theoretical, it was measurable, repeatable, and accelerating. Observers began to realize that the system was not failing. It was working beyond known limits. As production intensified, pressure expanded across the entire industrial network. By late 1942, Kaiser's operations had scaled to 7 major shipyards across California, Oregon, and Washington. Workforce numbers approached 196,000, including over 40,000 women and tens of thousands of African American workers employed in skilled technical roles. Training pipelines reduced specialization time from 4 years to as little as 2 weeks for welding tasks. Labor efficiency improved dramatically, from 1.1 million worker hours per ship to under 500,000. Material flow synchronized across rail systems, fabrication zones, and assembly lines. The system was no longer experimental. It had become a fully integrated industrial organism operating at national scale. The contrast between old and new systems revealed the true nature of the transformation. Traditional shipbuilders relied on generational skill transfer and apprenticeship systems, sequential dependency between construction stages, rigid adherence to detailed engineering specifications. Kaiser's system replaced this with rapid task-specific training, parallel production eliminating bottlenecks, flexible design tolerances enabling speed over precision. This was not an improvement of shipbuilding, it was a replacement of its underlying logic. The conflict was no longer between nations, but between industrial philosophies. It was during this expansion that senior officials began to grasp the implications. Howard Vickery, initially a critic of simplified designs, recorded a shift in position by mid-1942 as production output exceeded traditional yards by 70%. The realization was direct. Perfection delayed delivery, while adequacy multiplied capacity. Ships that met minimum operational standards but were produced in massive numbers would carry more cargo, sustain more supply routes, and ultimately determine strategic outcomes. The conclusion spread rapidly through military and industrial leadership. By early 1943, the system had reshaped American maritime production entirely. 18 shipyards adopted prefabrication and welding techniques. Output reached 3 Liberty ships per day. Total production climbed toward 2,710 vessels, each capable of carrying over 10,800 tons of cargo. The United States was no longer reacting to losses, it was overwhelming them. German submarine warfare, once a strategic threat, began to lose effectiveness as replacement rates exceeded destruction rates. The broader conclusion extended far beyond shipyards. This transformation demonstrated that modern war had shifted into the domain of industrial mathematics. Victory would not be determined solely by battlefield tactics or individual heroism, but by the ability to produce, replace, and sustain forces at scale. The Liberty ship program revealed that industrial capacity, measured in tons, hours, and output rates, had become the decisive factor of global conflict. September 1942, Portland, Oregon. At the yards of the Oregon Shipbuilding Corporation, thousands of workers moved in synchronized shifts around a half-finished hull, floodlights cutting through coastal fog, as cranes swung 100-ton sections into place with mechanical precision. Edgar Kaiser stood on an elevated platform, tracking progress against the clock, measuring not craftsmanship, but minutes. Across the Pacific coast, his rival in California, Clay Bedford, was doing the same. Neither man knew that within weeks, their internal competition would escalate into a production race that would push shipbuilding beyond anything previously recorded. What began as efficiency would turn into acceleration. What followed would redefine the limits of industrial speed. At that stage, both management and workforce shared a growing belief. The system could always go faster. The logic seemed justified. Each completed vessel required fewer hours than the last. Training pipelines were producing functional welders in 10 to 14 days. Prefabrication eliminated delays between construction stages. With every ship, confidence increased that output could continue rising indefinitely. Production managers calculated that incremental improvements, better coordination, tighter scheduling, increased shift overlap, could reduce timelines further. No one yet recognized the threshold they were approaching. Structurally, the system had reached a level of optimization rarely seen in wartime industry. It included 7 major shipyards operating simultaneously across 3 states, continuous 24-hour production cycles divided into 3 shifts, specialized labor segmentation reducing tasks to repeatable actions, supply chains delivering steel, engines, and components with minimal delay, crane networks capable of assembling entire ships from prefabricated modules. Numerical projections suggested that, with perfect coordination, assembly time could theoretically fall below 2 weeks per vessel. The numbers supported the belief. Output was limited only by organization. Then anomalies began appearing in production reports. Individual yards started outperforming system-wide averages by significant margins. Oregon reported construction times approaching 15 days. Richmond reduced assembly intervals between major sections to under 12 hours. Workers began exceeding planned output quotas by 20 to 30%. Supervisors noted that experienced crews were no longer the limiting factor. Coordination between units was. These deviations initially appeared as isolated improvements, not indicators of systemic transformation. The realization came suddenly. In September 1942, the SS Joseph N. Teal was completed in just 10 days, an achievement that cut previous records nearly in half. The number was not theoretical, not projected, but real. A full ocean-going cargo ship, assembled and launched in less than 2 weeks. The event triggered immediate reaction across the industry. Traditional shipyards dismissed it as a staged demonstration, a publicity stunt designed to attract attention rather than represent sustainable production. But internally, within Kaiser's organization, the interpretation was different. If 10 days was possible once, it could be repeated. Pressure intensified rapidly. Competition between yards transformed from informal rivalry into structured acceleration. Newspapers began publishing production times like race results. Supervisors reorganized shifts to eliminate downtime entirely. Workers pushed beyond standard output, driven by both incentives and the growing belief that limits were artificial. By October 1942, multiple yards were attempting to break the 10-day barrier, compressing schedules further with each attempt. The system was no longer stabilizing, it was accelerating under its own momentum. The underlying conflict now became visible. Traditional shipbuilding operated under constraints of sequence, precision, and controlled pacing. Kaiser's system functioned on scale, repetition, and speed. Where one required perfection at each stage, the other tolerated imperfection in favor of completion. This was no longer an industrial improvement, it was a direct confrontation between 2 incompatible models of production. It was at this point that Emery S. Land made a critical observation during a visit to Richmond. While acknowledging improvements, he remarked that even the fastest ships still lagged behind what mass production had achieved in other industries. The comment was brief, almost casual. But within the yard, it was interpreted as a challenge. Clay Bedford responded immediately with a proposal that would test the absolute limits of the system. Build an entire Liberty ship in under 10 days, cutting the existing record in half. Approval was granted under one condition. The attempt could not disrupt regular production output. The decision carried significant risk. Over 1,000 workers would need to operate in perfect coordination. Every component had to be prefabricated in advance. Any delay in material flow, crane operation, or assembly sequencing would collapse the schedule. The margin for error was effectively zero. By early November 1942, preparations were complete. Every section of the ship, bow, stern, cargo holds, engine assembly, had been constructed, inspected, and staged before assembly began. The system reached its highest level of synchronization. What had previously been production became execution. On November 8 at 0:01 hours, construction began. Within 96 hours, the hull was complete. Within 110 hours, the engine was installed. Within 4 days, 15 hours and 29 minutes, the ship stood ready for launch. The threshold had been crossed. November 12, 1942, 15:30 hours. Richmond, California. Before a crowd of military officials, industrialists, and skeptical competitors, the SS Robert E. Peary began to move. Its 441-foot hull, weighing over 28,000 tons, slid down the greased launching ways into San Francisco Bay. The entire structure, keel, engine, superstructure, and cargo holds, had been assembled in just 4 days, 15 hours, and 29 minutes. Clay Bedford stood among the supervisors, watching not with celebration, but calculation. He understood what the observers were only beginning to grasp. This was not a record. It was proof that the limits of industrial production had been miscalculated. Within days, this single demonstration would force an entire industry to abandon centuries of accumulated doctrine. Until that moment, maritime authorities had believed that speed beyond a certain threshold inevitably produced structural weakness. Welding at scale was considered unreliable. Simplified blueprints were seen as dangerous. Untrained labor was assumed incapable of precision work. These assumptions had governed shipbuilding for generations. Yet the vessel now floating in the bay contradicted all of them simultaneously. It was complete. It was functional. It was ready for service within 7 days, 14 hours from keel laying. The expectation that speed and quality were mutually exclusive had collapsed in a single afternoon. The system that made this possible had reached maximum compression. Every component of the ship had been pre-built before assembly began. The bow section alone consisted of over 50 individual parts, fully welded and equipped with anchor systems and crew compartments. The stern included installed propulsion shafts and steering mechanisms. For cargo holds, each weighing hundreds of tons, had been constructed as independent modules. The 140-ton engine, produced by industrial plants hundreds of miles away, arrived fully assembled and tested. When assembly began, cranes did not build the ship, they connected it. The entire process resembled final assembly rather than construction. Initial reactions from traditional shipbuilders followed a predictable pattern. Some dismissed the result as a staged demonstration, arguing that such speed could not be replicated under normal conditions. Others questioned long-term durability, pointing to potential weaknesses in welded joints. A minority recognized the deeper implication. If this process could be repeated even at reduced speed, it would render existing shipyards obsolete. The debate lasted days. The data resolved it. As production reports accumulated, replication became undeniable. Kaiser's yards began producing ships in weeks rather than months. Other American shipyards, under pressure from the United States Maritime Commission, adopted prefabrication and welding techniques. By early 1943, construction times across the industry had fallen to an average of 42 days. The record was no longer the exception, it was the direction. The scale of transformation intensified rapidly. By mid-1944, American shipyards were launching approximately 3 Liberty ships per day. Total output exceeded 2,700 vessels by war's end, representing over 53 million tons of cargo capacity. Workforce numbers peaked near 196,000 in Kaiser's yards alone. Labor hours per ship dropped from 1.1 million to under 500,000. Costs stabilized despite increasing wages and material demand. The system had achieved not only speed but efficiency at scale. The contrast between opposing industrial systems now became decisive. Germany's war economy, constrained by resource shortages and fragmented production, could not match the volume. Submarine warfare, once capable of crippling Allied logistics, became mathematically insufficient. Even at peak effectiveness, U-boats could not sink ships faster than they were being built. The equation had reversed. Losses no longer threatened supply, they were absorbed by production. It was in this phase that strategic understanding shifted among Allied leadership. Chester W. Nimitz would later summarize the reality. The war across the Pacific and Atlantic was sustained not only by fleets and armies, but by the continuous flow of material enabled by ships built faster than they could be destroyed. The battlefield extended into factories, shipyards, and assembly lines. Industrial output had become a weapon. By 1945, the results were measurable in final terms. Of the 2,710 Liberty ships constructed, only approximately 200 were lost to enemy action, a loss rate of 7.4%. The remaining fleet sustained Allied logistics across multiple theaters simultaneously. Many vessels remained in service for decades, disproving early concerns about durability. The system had delivered both speed and reliability, invalidating the final objections of traditionalists. The conclusion extended beyond shipbuilding or even the war itself. This transformation demonstrated that industrial capacity is not fixed. It can be expanded, reorganized, and accelerated when constraints are removed. The Liberty ship program proved that mass production, when applied to complex systems, can overcome not only enemy action but the limitations of conventional thinking. The lesson was precise and irreversible. Wars are not won solely by strategy or battlefield success, but by the ability to produce, replace, and sustain forces at a scale the enemy cannot match. 1943 to 1944. United States Industrial Network. What began as an experiment in a handful of West Coast shipyards expanded into a nationwide production system that operated with the precision of a machine and the scale of an entire civilization. Across 18 shipyards, Liberty ships were no longer exceptional achievements, they were routine output. Henry J. Kaiser no longer needed to prove his methods worked. The system had already escaped his control and become national doctrine. What he had built was no longer a shipbuilding program. It was an industrial weapon. At this stage, Allied command operated under a new assumption. Shipping losses no longer determined strategic limits. German U-boats continued to operate across the Atlantic, but their impact had changed fundamentally. Even at peak efficiency, they could not keep pace with American production. Where earlier calculations had measured survival in terms of tonnage lost versus replaced, new projections showed consistent surplus. The expectation shifted from defensive replacement to offensive expansion. Supply lines were no longer fragile, they were multiplying. The system sustaining this output had reached full maturity. It included 18 shipyards operating standardized Liberty ship production, over 2,700 vessels planned and executed between 1941 and 1945. Average construction time reduced to 42 days. Peak output of nearly 3 ships per day. Total workforce exceeding 600,000 across all supporting industries. Steel production exceeding 700,000 tons annually in dedicated facilities like Fontana. Every element of the process, from raw material extraction to final assembly, was synchronized. Delays were no longer systemic. They were anomalies. Yet even within this system, early warning signs of deeper transformation began to appear. Production no longer depended on experience. Workers trained in weeks were performing tasks once reserved for master craftsmen. Women, comprising up to 27% of the workforce in some yards, operated cranes, welded hulls, and supervised assembly lines. African American workers filled skilled technical roles at a scale unprecedented in American industry. Traditional labor hierarchies, built over generations, were dissolving under the pressure of efficiency. Initially, this appeared as a temporary wartime adaptation. Then the scale of change became undeniable. By mid-1944, American shipyards were producing more tonnage than the rest of the world combined. Approximately 53 million tons of shipping capacity had been created within 4 years. Entire fleets could be replaced faster than they were destroyed. Ships that had been designed with a lifespan of 5 years continued operating decades later. The system was not only producing faster, it was producing sustainably. With each passing month, the imbalance between opposing sides intensified. Germany's industrial base, constrained by resource shortages, strategic bombing, and fragmented logistics, could not match the output. Fuel shortages limited production. Transportation networks were disrupted. Even when new weapons or vehicles were produced, delivery to the front became increasingly difficult. In contrast, American production expanded continuously, supported by secure supply chains and virtually unlimited access to raw materials. The conflict between systems reached its clearest expression in simple arithmetic. One side measured output in individual units, tanks, ships, aircraft. The other measured output in rates, units per day, per week, per month. The difference was not quantitative alone. it was conceptual. Germany optimized performance. The United States optimized throughput. Over time, throughput overwhelmed performance. It was during this period that senior military leaders fully understood the implications. Chester W. Nimitz would later describe the Pacific Campaign as a logistical victory as much as a military one. Operations across distances exceeding 5,000 miles required continuous resupply. Fuel, ammunition, vehicles, and food, all delivered by ships built in American yards. Without that flow, no offensive could be sustained. With it, operations could expand indefinitely. By late 1944, the outcome had shifted from uncertainty to inevitability. German forces faced not only military opposition but a production system they could not disrupt. Bombing campaigns damaged factories, but new facilities replaced them. Submarines sank ships, but replacements arrived faster. Tactical victories no longer translated into strategic advantage because losses were absorbed immediately. The system had removed scarcity from the equation. The final accounting of the Liberty ship program revealed the scale of transformation. 2,710 ships built. Over 800 produced by Kaiser's own yards. Construction time reduced from 230 days to 42. Labor hours cut by more than 50%. Loss rates under 8%. Thousands of vessels remaining operational decades after the war. These numbers were not simply statistics. They were proof that industrial organization had become the decisive factor of modern conflict. The conclusion reshaped global understanding of warfare. Victory no longer depended solely on strategy, leadership, or battlefield execution. It depended on the ability to sustain operations indefinitely through production. The Liberty ships demonstrated that when industry reaches sufficient scale, it transforms from support function into primary weapon. This was the final realization. The war was not only fought on land, sea, and air. It was fought in factories, shipyards, and assembly lines, and it was decided there. 1945, post-war assessment. Across the ruins of Europe and the Pacific, military analysts began reconstructing the true mechanics of victory. Battles had been fought across continents, millions had been mobilized, and entire cities had been destroyed. Yet when the numbers were assembled, production totals, transport capacity, supply throughput, a different picture emerged. Henry J. Kaiser was no longer seen as an outsider who disrupted shipbuilding. He was recognized as the architect of a system that redefined how wars were won. What had started as an emergency response in 1940 had become, by 1945, a model for global industrial power. During the final months of the war, Allied command no longer calculated risk in terms of supply shortages. Instead, they calculated how quickly resources could be concentrated at any given point. Liberty ships continued to deliver cargo across every theater. Fuel, ammunition, vehicles, food, at volumes that eliminated logistical constraints entirely. A single vessel could carry 10,800 tons of cargo, 2,840 jeeps, 440 tanks, or 230 million rounds of ammunition. Multiplied across thousands of ships, this created a continuous flow of material that no opposing force could interrupt. The industrial system supporting this output extended far beyond shipyards. It included steel production facilities like Fontana delivering hundreds of thousands of tons annually, engine manufacturing plants producing standardized propulsion systems at scale, rail networks moving prefabricated sections across thousands of miles, training systems converting unskilled labor into functional specialists within weeks, healthcare systems, including the foundations of Kaiser Permanente, sustaining a workforce of nearly 200,000 workers. Each component operated not independently, but as part of a synchronized national mechanism. Yet even as production peaked, new signals emerged that the transformation extended beyond wartime necessity. The workforce itself had changed permanently. Over 40,000 women had entered heavy industry roles, performing welding, crane operation, and structural assembly. African American workers, previously excluded from skilled industrial positions, now operated in technical and supervisory roles across multiple facilities. Traditional labor structures, apprenticeships, guild systems, generational skill transfer, had been bypassed entirely. Initially justified by urgency, this shift proved sustainable under real production conditions. The scale of output reached levels that redefined industrial possibility. By the end of the war, American shipyards had produced over 5,500 vessels, totaling approximately 53 million tons of shipping. Of these, 2,710 were Liberty ships. Kaiser's yards alone accounted for 1,490 units, over 27% of total production. Construction time had fallen from 230 days to as low as 4 days in extreme cases, stabilizing at 42 days for standard production. Labor efficiency doubled. Costs remained controlled despite inflation. No previous industrial system had achieved this combination of speed, scale, and sustainability. In contrast, Axis production systems revealed structural limitations that could not be overcome. German industry, constrained by fuel shortages, fragmented logistics, and increasing Allied bombing, struggled to maintain output levels. Even when advanced weapons were produced, their impact was limited by insufficient quantities and disrupted supply chains. The imbalance was no longer tactical, it was systemic. One side could scale indefinitely, the other could not. Post-war analysis by military leaders confirmed the shift. Chester W. Nimitz emphasized that operations across the Pacific, spanning over 5,000 miles, were sustained not by isolated victories, but by uninterrupted logistical flow. Without continuous resupply, offensives would stall. With it, they expanded. The Liberty ships ensured that expansion never stopped. The final phase of the war demonstrated a principle that would define all future conflicts. Industrial capacity, when organized effectively, removes limitations on strategy. Armies can advance as far as supply allows. When supply becomes effectively unlimited, operational boundaries disappear. This was the condition the Allies achieved by 1944. After the war, the physical shipyards began to decline. Workforce numbers dropped from nearly 200,000 to under 20,000 within months. Facilities that had operated continuously for years fell silent. Yet the knowledge developed within them did not disappear. Prefabrication, modular construction, welding techniques, and parallel production became standard practices across global industry. Shipyards in Japan and South Korea would later adopt these methods, building the foundation for their dominance in global shipbuilding during the second half of the 20th century. The legacy extended beyond maritime production. Industrial engineering, operations management, and large-scale manufacturing systems incorporated principles proven during the Liberty ship program. Training models emphasizing specialization replaced traditional apprenticeships. Production planning shifted toward parallelization and scalability. The concept of mass production expanded from consumer goods into complex industrial systems. The deeper conclusion, however, was not technical, it was conceptual. The Liberty ship program demonstrated that perceived limits in production are often not physical constraints, but organizational ones. What had been considered impossible for centuries, building ocean-going vessels in days, was achieved not through new materials or radical technology, but through reorganization of process, labor, and scale. This story revealed a final, decisive truth. The outcome of World War II was determined not only by battles fought, but by systems built. Victory belonged to the side that could transform industry into a weapon, production into momentum, and logistics into inevitability. 1945 to 1950, global shipbuilding industry. In the years immediately following the war, silence settled over the same shipyards that had once operated without pause. Cranes stood idle. Assembly lines stopped. At Richmond, Portland, and dozens of other sites, production that had reached 3 ships per day collapsed within months. Yet beneath this apparent decline, something far more significant was unfolding. The methods pioneered under wartime pressure were no longer temporary solutions, they were becoming permanent foundations. Henry J. Kaiser had not just accelerated production. He had rewritten the rules of industrial organization. At first, many observers believed the system would disappear along with wartime demand. Traditional shipbuilders expected a return to pre-war practices: skilled labor, long construction timelines, and carefully controlled output. The assumption was logical. Emergency measures, by definition, were not meant to last. Without the urgency of war, there would be no reason to maintain extreme production speeds. Shipbuilding, they believed, would return to craftsmanship. On paper, however, the advantages of the new system were too significant to ignore. The post-war industrial framework included modular prefabrication enabling simultaneous construction of major components, welding techniques replacing millions of rivets and reducing labor requirements, training systems capable of producing skilled workers in weeks instead of years, standardized designs allowing rapid scaling of production, integrated supply chains connecting steel mills, factories, and assembly yards. Every metric favored the new model. It was faster, cheaper, and required fewer highly specialized workers. The first indications of long-term change appeared in reconstruction efforts across Europe and Asia. War damage required rapid rebuilding of infrastructure, fleets, and industrial capacity. Nations that had observed American production methods during the war began adopting similar approaches. Japanese and South Korean shipyards, rebuilt in the 1950s and 1960s, implemented prefabrication and modular assembly as core principles from the beginning. What had been revolutionary in 1942 became standard practice within a decade. Then the scale of transformation became global. Shipyards that adopted modular construction began outperforming traditional facilities in both speed and cost. Construction timelines continued to shrink. Output increased without proportional increases in labor. The competitive balance shifted rapidly. Countries that embraced these methods dominated global shipbuilding. Those that retained traditional approaches declined. The contrast between systems persisted, but now in peacetime industry. Traditional shipbuilding emphasized precision, customization, and craftsmanship. The new model emphasized efficiency, standardization, and scalability. One produced fewer specialized vessels. The other produced large numbers of reliable ships at predictable cost. Over time, the latter proved economically and strategically superior. It was during this period that industrial theorists began to formalize what had occurred during the war. Analysts studying production data concluded that the Liberty ship program had demonstrated a fundamental principle. Industrial capacity is not a fixed resource, but a variable that can be expanded through organization. Constraints that appeared physical, time, labor, complexity, were often the result of outdated processes rather than actual limitations. By the 1960s, the influence of these methods extended far beyond shipbuilding. Construction, automotive manufacturing, heavy industry, and even aerospace adopted principles of modular design and parallel production. Training systems shifted toward specialization, reducing the need for long apprenticeships. Management strategies prioritized throughput over perfection. Entire industries reorganized around the concept of scalable production. The long-term impact was measurable in global output. Shipyards using modular construction produced vessels faster and at lower cost than any previous system. Industrial productivity increased across sectors that adopted similar methods. The gap between traditional and modern production systems widened until one effectively replaced the other. What had begun as a wartime necessity had become a universal model. The final understanding emerged gradually but definitively. The Liberty ships themselves were not the most important outcome. Many were scrapped, others repurposed, and only a few preserved. Their physical presence faded. What remained was the system that created them. This story demonstrated a lasting truth. Progress does not come from refining existing methods, but from redefining them. Wars may accelerate innovation, but the transformations they produce extend far beyond conflict. The real legacy of the Liberty ship program was not measured in ships launched, but in limits removed. Industrial power, once unleashed, does not return to its previous state. 1970 to 2000 Global Industrial Analysis. Decades after the war, when the numbers were no longer classified and the urgency had faded, historians and engineers began reconstructing what had truly happened between 1941 and 1945. The conclusion was no longer debated. The Liberty ship program had not simply accelerated production. It had exposed a flaw in how industrial limits were understood. Henry J. Kaiser had demonstrated that constraints assumed to be physical were, in reality, organizational. At the beginning of the war, shipbuilding capacity had been measured in months per vessel. By its end, it was measured in output per day. This shift from unit-based thinking to rate-based thinking became the defining transformation. Industrial systems were no longer evaluated by how well they built a single product, but by how consistently they could produce at scale. The difference was subtle but decisive. One approach optimized quality. The other optimized victory. The analytical framework that emerged in post-war decades identified several core components behind this transformation. Parallel production replacing sequential dependency, specialization of labor reducing training time from years to weeks, modular design allowing independent construction of complex systems, redundancy in resources compensating for inefficiency, centralized coordination combined with decentralized execution. These principles, once considered incompatible with complex manufacturing, became the foundation of modern industry. Early resistance to these ideas persisted, particularly in industries rooted in tradition. Critics argued that such methods sacrificed craftsmanship and long-term reliability. Yet the data contradicted them. Liberty ships, expected to last 5 years, often operated for decades. Industrial systems built on these principles proved not only faster but durable. Efficiency did not eliminate quality. It redefined how quality was achieved. The broader implication extended into military doctrine. Analysts concluded that modern warfare had shifted irreversibly into the domain of production economics. The decisive factor was no longer the strength of individual units, but the ability to replace losses faster than they occurred. Attrition, once a tactical concern, became a mathematical certainty. The side with greater industrial throughput would inevitably prevail. This realization reshaped strategic planning during the Cold War. Both superpowers invested heavily in industrial capacity, logistics networks, and production scalability. Military strength was measured not only in active forces, but in the ability to mobilize, produce, and sustain operations over time. The lessons of the Liberty ships became embedded in doctrine, influencing everything from supply chain design to weapons manufacturing. At the same time, industrial leaders began applying these principles beyond military contexts. Automotive production expanded using modular assembly lines. Construction adopted prefabricated components. Electronics manufacturing scaled through standardized processes. The concept of mass production evolved into systemized production, where complexity was managed through organization rather than expertise alone. The most important shift, however, occurred in mindset. Before the war, limits were accepted. After the war, they were questioned. Engineers, managers, and planners began to treat constraints as variables to be tested rather than boundaries to be respected. This change in thinking proved more influential than any specific technology. By the late 20th century, the influence of these ideas could be seen globally. Shipyards in Asia dominated world production using modular construction. Manufacturing systems operated continuously across multiple continents. Supply chains extended thousands of miles while maintaining precision and efficiency. The principles first proven under wartime pressure had become universal standards. The final conclusion, drawn from decades of analysis, was simple but profound. Industrial power determines the outcome of large-scale conflict. Tactics, leadership, and technology remain critical, but they operate within the limits set by production and logistics. When those limits are expanded, everything else changes. The Liberty ships themselves were only the visible result. The true revolution was invisible, a transformation in how humans organize effort, scale production, and redefine what is possible. 2000 Present modern global industry. By the beginning of the 21st century, the transformation that began in wartime shipyards had reached its final stage. It was no longer recognized as innovation. It had become invisible, embedded so deeply into industrial systems that few remembered its origin. Container ships stretching over 400 meters in length were assembled from prefabricated sections built across multiple continents. Entire aircraft were produced through distributed manufacturing networks. Supply chains operated continuously, moving materials across oceans with precision measured in hours. The principles first proven in 1942 had scaled to a planetary level. At this stage, industrial planners no longer questioned whether complex systems could be built rapidly. The question had shifted to how fast global systems could adapt. Production was no longer tied to a single location. Components manufactured in Asia, Europe, and North America converged into final assembly points with minimal delay. The system included modular production across international networks, real-time logistics coordination tracking millions of tons of cargo, automated manufacturing reducing dependence on manual labor, standardized components enabling interchangeability at global scale, continuous production cycles operating without interruption. What had once required thousands of workers in a single yard now operated across entire continents. Early warning signs of this final transformation appeared in the late 20th century, but their full implications became clear only with digital integration. Information systems allowed production, transport, and assembly to function as a single synchronized process. Delays that once halted production for days were reduced to minutes. Inventory systems predicted demand before shortages occurred. The same principle that allowed Liberty ships to be assembled from prefabricated sections now operated globally, only faster, larger, and more precise. Then the scale became unmistakable. Modern shipyards began producing vessels exceeding 200,000 tons displacement using modular construction methods directly descended from wartime innovations. Aircraft manufacturers assembled complex machines from millions of parts produced worldwide. Automotive plants produced vehicles in minutes rather than days. The numbers exceeded anything imaginable in 1942, not because of entirely new technology, but because the underlying system had been refined and expanded. The contrast between past and present industrial logic revealed the final shift. Earlier systems were constrained by location, labor specialization, and sequential production. Modern systems operated on distribution, automation, and parallel execution. One required concentration. The other thrived on scale without boundaries. This was no longer industrial production, it was industrial ecosystems. At this point, analysts recognized the ultimate implication. The same principles that had determined victory in World War II now defined global economic power. Nations capable of organizing production at scale, integrating resources, labor, and logistics into unified systems, held decisive advantage. Military strength, economic influence, and technological leadership all depended on the same foundation: the ability to produce and sustain. The realization echoed the conclusions drawn decades earlier, but at a far greater scale. The Liberty ship program had proven that industrial output could exceed destruction. Modern systems extended that principle further. Output could exceed demand, reshape markets, and redefine global balance. The final conclusion remains unchanged, only magnified by time. Large-scale outcomes, whether in war or in peace, are determined not by isolated achievements, but by systems capable of sustained, scalable production. What began in the shipyards of Richmond did not end with the war. It became the blueprint for the modern world.